2, 1. Okay, go.
All right, thank you. Okay, good evening again, Dr. Yogi, and to all of the students here. It's nice to finally have this session again for quite a long time, but it's really good to be back here. So for today, we're going to talk about random forest classifier. But before we go into the random forest classifier, its primary principle will revolve around decision tree. So random forest, mm, my handwriting is really poor, so I'll just
Wow, you're like Dr. Hera now.
my handwriting is very poor. I'll just type it like
Just
this.
type it, it's fine.
Random forest classify. Right. And once we already know what decision tree is, later on we'll also get to realize that they do have a lot of similarities when it comes to random forest classifier, because it would be very difficult for us to jump into the random forest because the primary principle of random forest classifier will revolve around decision tree. Mm, Okay, so for the terms in decision tree, it primarily revolves around the tree itself. So for example, in tree we have the root nodes. So if the tree has the root on in the lowest part of the overall part of the tree, in the decision tree or random forest classifier, it's located in the topmost part. And that's what we call as root node. So it is called as root node regardless of how your tree looks like. And in tree, you also have branches. So for example, we have branches over here that holds our leaves. And this is also our branches. And then, but we have what we call as leaf node or internal node. So also decision node. Oh, sorry, not leaf node, internal node and decision node. The internal node and decision node holds if in the tree part it holds all the trees before the ending part of your trees. So this part and not this part. These are what we call as internal nodes or decision nodes. So somewhere hiding within those leaves. And then we also have again small branches, and then that's where leaf nodes come in. So the leaf nodes are the ending parts of your trees. Leaf nodes also called as terminal nodes. So that's for the terminology of our decision tree and random forest classifier. And in random forest classifier, we have different kinds of algorithms. So we have cart decision. The most common one is cart ID 5, cart ID 4, or hands, and also hands algorithm. But for the coding part, this is the most common one and the most easy among all the different types of algorithm behind the decision tree and random forest classifiers. So we'll just discuss the Hans algorithm. So in Hans algorithm, specifically using our random forest tree and decision tree classifier, we have these factors. So in the Turkey earthquake, your factors would be your latent variables. So these pertain to your latent variables. And for this one, it's what we call as the target variable. Target variable, so in the data that Doc Yogi mentioned that Doc Yogi sent to me, those are the two target variables that we have: intention to visit if or intention to donate to Turkey
Both,
earthquake
yes.
victims as an
Visit and
intention
donate.
to visit. Okay. So those are the target variables for Hans algorithm. But for our example, we'll just utilize one target variable. So you can also add another one target variable here, because in coding, we can just, for example, we have ID over here, and then you also wanted to check both. So in the coding part, we can just eliminate IV first, and then evaluate your latent variables or your features depending on your intention to donate. Then after you've completed your decision tree for intention to donate, we're going to compare our variables to the intention to visit. Mhm. Okay, so for example, so how do we compute it? So this is very good, a very good example, because in one of your research papers you really have to check how can you really wanted to elaborate on how you can explain the tree elaborately, because in your trees, especially in the data, you'll have many branches. So it's not like just this one. It's not like having one branch here and then three branches over here. In your data, you might have, let's say, if you have um how many was it? Let's say seven. If you have seven latent variables, then you'll also have seven branches as your starting point. So 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. And then for every seven latent variables, you'll also have another nodes, internal nodes within them, because you're going to connect these latent variables into another latent variable. So it's a form of combination among all of them. Okay, so for example, if you're going to explain it, since we have different classes, so in random forest, these are what we call as classes. In classes, we may have at least two, so you can have no, you can have yes. In our example, in our data rather, we may have 1, 2, 3, 4, 5, and it's completely okay. But for easier explanation, we can just mention no and yes for this example. Mhm. Okay, so the first step is always to find, or to always have your target variable at the topmost part, because that's what we wanted to elaborate and to explain in the latter part, or in the latter part of our results and findings discussion. So you just have to input how many yes and how many no you have, or in your example, you just have to input how many ones, how many twos, how many threes, fours, and fives do you have. So for yes, we have 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then for no, we just have to count it 1, 2, 3, and 4. That's how we calculated this yes and no. And remember again, this is for play golf for the topmost part. And the next step for us is to choose our attribute, or also known as features, or your latent variables. So these are your features or your latent variables or attributes. And let's just say you were going to utilize Outlook. In Outlook, we have three different options. So we have rainy, this one rainy, overcast, and sunny. That's why we have three branches over here, rainy, overcast, and sunny. So the next step is almost similar to the previous one. So we just have to count how many yes and how many no for each of your internal nodes. So let's say rainy, rainy, we'll just have to find what are, or how many counts do we have for rainy. Rainy for no, we have one, two, no, rainy, two, three, and then rainy, uh, we only have three. So we have three, we'll count it. And then for the rest, we have rainy, yes, one, and rainy, yes, two. So if we have values that let's say if both of your classes have values, then you have to continue your branch. So that means we'll have to continue this branch, because that means you still have some indecisions within the group. Because in the decision tree, we have to come up with an answer that goes through with the similarities. So we wanted to find how can we end the decision tree. So it will only end if, let's say, we have no yes, but we still have no, or we have no no's, but we still have yes. So for the overcast, let's say for an example, overcast, it has one yes, another one for yes, third for yes, and then fourth one for yes. So that means you have four yeses for overcast, but we don't have any no in the overcast outlook attributes. So that means we don't need to branch out our overcast. And how about for sunny? For sunny, we have one, two, three yes, and then we only have one no. So we also have to branch out this one. Okay. And then let's continue our decision tree. So a while ago, we mentioned that we have to branch out rainy and then sunny, but not for overcast. So we're going to stop in the overcast, but instead we can just say yes. So what does this mean? For example, um, a player wants to play, what was this? A player wants to play baseball. That player will only play baseball if the outlook is overcast. So automatically it will not play if the outlook is not overcast. And then let's branch out again. This time let's just say we're going to choose temperature. So after outlook, our next branch node would be temperature. So this will be temperature, and under temperature we have hot, mild, and cool. So we also have three branches, hot, mild, and cool. So for this one, we should also have hot, mild, and cool. So this should be hot, mild, and cool. So for hot, let's say we're going to count how many yes and no's for hot. We have one, two, three. So no would be three, and then yes would be one and two. What? Okay. How about for mild? Mm, For mild, let's count this again. Mm, One yes, two yes, three yes. So we have three yes for mild. Oh, sorry, I forgot to mention rainy. It should be rainy, temperature hot. So let's count again. Mm, It should be rainy and then hot. So this one, rainy, hot, and then no, we have one. Rainy, hot, and then no, we have two. So we don't have any more combinations when it comes to rainy, hot, and no. So that means rainy, hot, and no, we have two. For yes, we don't have any other combinations that entail rainy, hot, and yes. That's why we can just stop over here. So that means we won't need to branch out this one, rainy, hot, and another branch. So we can just stop here. How about for rainy, mild, and yes or no? Let's see this one. So rainy, mild, and no. So we have one. How about for this one? Rainy, mild, and yes. So we also have one yes. So if we have both values for all of these classes, then we still have to branch out this one. And lastly, we have rainy and cool. So this is the last one, rainy and cool. Then we only have one. So since we only have one yes and zero no, we don't need to branch out this part. So next, how about for humidity? So if we can still recall from the previous slide, we don't need to branch out this one. We also don't need to branch out this one because we have zero yes here, and then we have zero no's here. So if we're going to interpret it, the baseball player would only play the ball if the weather is rainy and the weather is cool. And there is a high possibility for that player not to play any kinds of ball games that he wants if the weather is rainy and the weather is hot. Okay. How about for humidity? For humidity, we only have, let's say, rainy, mild, and high. So let's focus on rainy, mild, and high. We have one nose. So one nose, we don't have any yes anymore. And for the other one is rainy, mild, normal, and yes. So this one, rainy, mild, normal, and yes. So we don't have any nose for this part. That's why we also have to stop. And again, if we're going to interpret it, the player will play the game. If the outlook is rainy, the temperature is mild, and the humidity is normal. But if the humidity is high, most likely the player won't engage in the game. And let's say for the third node. So a while ago we mentioned that we don't need to branch out this one, the overcast, so we'll just leave it out. But how about for the sunny? Since we have three different outlooks, rainy, overcast, and sunny, we also have the continuous sunny. So if you have another outlook here, so since you have many variables, you have to keep branching out all the variables in the latent variables. Okay, so for temperature, we have mild and cool under sunny. Only mild and cool. That's why we only branched out into two. So for instance, so sunny, mild, yes, we have one. Oh, let's focus on cool first. So cool, sunny, cool, yes. So we have one yes. We also have sunny, cool, and no. We also have one no. So this meant that we have to branch out in the next iteration. For sunny and mild, this one, sunny, mild, and yes. And we also have another sunny, mild, and yes. That means we have two yeses here and zero no. So we just have to stop branching out this part. So some of the baseball players may also play golf if their outlook is sunny and the temperature is mild. So just to continue the cool weather, so next is to identify sunny, cool, and true or false for the windy part. So sunny, cool, and then normal. Mhm. Oh, this should be mm, no. Mm, oh, this should be like this. The PowerPoint is incorrect, so I'll just put one here. So the next one should be windy. Hmm? Oh, sorry, humidity. Humidity.
Humidity.
Mhm. The PowerPoint states windy. Okay, so we should remove that part. So humidity should be normal. Okay, so sunny, cool, this one. We just have to focus on this part because we're talking about sunny, cool, this one. Sunny, cool, and normal. Since we only have one humidity here, we only have normal, we can just remove this part. Then we'll just treat this as normal. But your normal has yes, and one no. So if we still have one yes and one no, then that means we still have to branch out this part. And then the next time that we branch out, we're going to utilize windy because we've already finished outlook, temperature, and humidity. So the next one would be windy. For windy, we have true, we have true and false. So technically, we only have one yes. So play golf, one yes over here. Oh, sorry, true is no, this one, because true is no, and then false is yes. So if we're going to interpret this line, it's going to be the player will only play if the outlook is sunny, the temperature is cool, the humidity is normal, and the wind and it's not windy because it's false. And yes, so most likely the player will change his mind if the wind is very high, let's just say, if it's very windy. So that's how we can interpret the decision tree. But how can we identify which attribute comes first? So for example, can we utilize temperature first before outlook? So we can just say temperature and then branch it out into hot, mild, and cold. And then in the next branch and node, we can say outlook. This is possible by utilizing other kinds of algorithms behind the decision tree and random forest classifier. It's about finding or applying your node impurity and then finding how impure your probability is. So we have three primary types, but I would only recommend Gini index and entropy. So in the coding, we'll just have to replace entropy into Gini or Gini into entropy so that we can no longer follow this formula, but this is the formula that you can also include in the research paper. Usually, misclassification error is not utilized simply because it's not a good evaluation when it comes to the impurity of our nodes. So how
I've
can
never
we
seen
compute
that.
the misclassification?
I don't know. I only see Gini index and entropy
Mm,
usually.
yes. Misclassification error is not that popular. Okay. And then, so in our Gini index, and even in almost every type of our impurity method, we have what we call as impurity measure or P, which is our parent, and then impurity M, which is parent minus the child or the offspring. And then we can calculate gain by subtracting the impurity of parent and offspring. So just for an example, so let's say we have this example. So this is your yes. So for example, this is your yes, and then this is your no from the first, for example, this is Outlook, and then we have three branches here, and then we have yes over here, and then no over here. So this would pertain to this one, and then the other one would pertain to another figure, and then the other one would be pertaining to this one. So it's okay if they're not arranged properly as long as the computation is correct. So for the classes yes and no, this is just an example. Let's just say this is yes and this is no. we can just follow this formula. So 1 minus the probability of your data. So that would be 1 minus this one. So 0 over 6, we can just compute the probability first. So 0 over 6. 0 over 6 came from the total of 0 divided by the probability of all the occurrences in this node or in this branch node. This is your P of C1 and then this is your P of C2. So that's why this pertains to 0 over 6 and the other one would pertain to your 6 over 6. So we'll just apply the probability principle. And how can we apply the Gini method? Simply by applying these formulas. So 1 minus 0, this one. So 1 minus 0, and then minus your P of C2. Sorry, that's 1. So 1 minus 0 minus 1 is equivalent to 0. So usually the impurity is already equivalent to 0 if one of the classes is equivalent to 0. So if it's 0, if the other one is 0, then most likely your gene impurity is also equivalent to 0. Simply because in the impurity, we wanted the lesser value. Because in impurity, it's like our determiner in order for us to find what kind of value would lead us to the lesser error for the classification part.
It's like
And
Gini
then
index of the rich and poor, like we
mm,
want it to be like as no gap, like smaller as possible, like that.
yes, that's a good metaphor. And then how about for the other one? So you have to compute the Gini index node of each node. So if you have 100 nodes, you have to compute all of them. For the other one, we have 1 minus 1 over 6 because the total is also 6. And then the total for here is also 6. So 1 minus 1 over 6 squared. Oh, sorry, I forgot to mention the squared part. We have squared minus 5 over 6. And then for the third one, that would be 1 minus 2 over 6. And then squared as well, minus 4 over 6. And then we'll in the end we'll be able to calculate these two. So among all these values, the best example or the best node would be this one. Only if we're talking about single node, it would have to be this one. So if in the outlook, let's say the we are required to mention what's the most important among all these indicators, then we have to mention this one because it has the least impurity. So technically, it will lead us to a greater classification in the end as we progress in the random forest classifier. But how can we apply this in the partitioning of our attributes? So for example, as we mentioned a while ago, we can pick not outlook in the first line, we can pick, let's say, temperature first before outlook. We can also choose humidity first before outlook. So it's a matter of finding the best sequence among all of them. And with the help of Gini index, entropy, or misclassification error. So for Gini index, we just have to apply the formula a while ago. So the 1 minus probability of squared and its summation. So for example, we have the parents. So again, when we say gain, we have this formula, the parent minus m, or the Gini of parent minus the Gini of your child or of the offspring. So in parent, this is your yes and no as well. This came from the value of, for example, we have the play, mm, the play golf, and then yes is 7, no is 5, and then it will branch out. So this is where the parent comes in. So we calculate this value by 1 minus 7 over the total 7 plus 5, that's 12. 1 minus 7 over 12 squared minus 5 over 12 squared. And then the value would be this one. And how about for your parents? So this is already your Gini index for the parent. So this is your parent. We've already calculated this part. And then how about for the offspring? So we can also calculate it by, again, identifying the yes and no for this part. So if we can still remember, aside from having yes and no here, for the play and golf, you also have another yes and no for each node. So for example, for your first node or N1, you have yes of 5, no of 1. And then for N2, we have yes of 2, and then 4 no's. So we just also have to follow the same formula a while ago and also similar to the parent. First, for the N1, 1 minus 5 over 6, 6 because the total of these N1 is equivalent to 6. Then minus 1 over 6 squared. And then the total value would be 0.278. And then the next one would be 1 minus 2 over 6. Why 6? Because the total of these values are 6, and then minus 4 over 6 squared. So you have the Gini of your first node and the second node here, but it does not stop there. So you have to calculate the weight of your Gini. So how can we calculate the weight of the Gini? So we just have to find the total value of this part, this one. So that its total is 6, and then the total of N2 is also 6. So if we add them, we have 12. So this one pertains to your N1, and then this one pertains to N2. So that means 6 over 12 times your N1, your Gini of N1, plus 6 over 12 again, because we have 6 here, multiplied to the Gini of your N2. So that's how we calculate 0.361. And then we just have to subtract the Gini of your parent, which came from this part, 0.486 minus 0.361, that's equivalent to 0.25. But if in node basis, what we're looking for is the least impurity. In gain, what we're looking for is the highest gain, because that means if it brings us the highest gain, then most likely it will lead us to lesser errors. So it's in a different scenario when it comes to evaluating our gains versus the pure impurity of our nodes. So for example, this is your value for outlook. And then we've calculated again, let's just say for temperature, we've calculated a new value of 0.5. Then we have to choose temperature over outlook. So in our decision tree, temperature should come first before the outlook. So this will be your outlook. But what if we have more than two latent variables or attributes? So for example, we also have humidity. So this is for outlook. And then temperature is zero 0.5. And then let's say humidity is higher than temperature. Let's say, for example, 0.7. So we have to create another one at the topmost part. So this will be your humidity. So we just have to arrange them based on the highest temperature, so in descending order. So humidity, temperature, and then finally outlook. So that's how you can also apply the explanation when it comes to the research paper, because in the actual code, it will just show the final solution. It will not reflect any kinds of explanations or any kinds of step-by-step procedure. So you really have to explain why did the humidity came first before the temperature, or why did the temperature came first before the outlook.
Don't worry, everyone. Later on, this one, the calculation it's done by the
Mm,
software.
yes.
Don't
Yes, that's
worry.
correct.
But the most important for all of you right now, I know all of you kind of like, oh, so full of math, but the most important for all of you, you need to understand. Can you go back again, Dr. Maela, for the
Oh,
previous slide?
yes.
Now this one. You have to understand what is 0.486,
Mm,
0.396, and then 0.125, This is the most important one. Okay. So because the value is always there, like they will calculate it for us. Okay.
mm.
Yeah.
Right, right. And some I've encountered one reviewer that asked not in the random forest, but in the ANN part, it asked a bit of some values when it comes to the coding part. So sometimes you really have to check on the values. Maybe
Yes.
we'll never really know what kind of
Yeah.
questions we might get asked.
Okay. So far, so good. All of you, Jimmy, you okay? Are you there? You're in Malaysia right now. Are you still alive? Okay. Just continue. Okay.
Mm, okay.
Jimmy, you still
All
alive?
right.
Okay. Okay.
Yes, I.
Yeah, okay. Okay. Good. Next. Okay.
Okay, going well. So next, how apart from splitting our attributes, so apart from splitting attribute outlook, humidity, what else? And any other kinds of attributes that we have, we can also identify how many splits or how many branches can we utilize. So for example, a while ago in we have rainy, sunny. Oh, I forgot the other one. Let's go back to the part. Okay, so for this one, let's say we have rainy, overcast, and sunny. What if I want to combine rainy and overcast? It's also possible, and sometimes the code would just combine them because they're more optimal than having three branches. Or we can also combine rainy and sunny, or we can just combine overcast and sunny. So a lot of probabilities can definitely happen here, but we can utilize again Gini index using that part. So using the same formula, we can just say in the coding part, these kinds of probabilities automatically happen. So it will automatically identify different kinds of combinations. So for example, we have family, sports, and luxury. We can also combine sports, luxury, and versus the family. So in the decision tree, it will be like this. We'll have three branches. For this one, we'll only have two branches. Also, two branches for this part. And we can calculate it by using the same formula again. So 1 minus, so we'll calculate the total first. So 1 minus 1 over 3 squared minus 8 over, sorry, 1 minus 1 over 3 squared minus, sorry, 1 minus 1 over 4
Four, four.
squared minus 3 over 4 squared. All right. And then for the other one, we also have to calculate it as 1 minus 8 over 8 squared minus 0 over 8 squared. And then same for the other one. And then we'll just have to calculate the sum of all the values. In the end, we'll receive these values 0.163, this one, and then this one. But if in gain, what we're looking for is the highest value, in splitting of Gini index, what we're looking for is the lowest value, very similar to the concept of the impurity method, which we've talked about earlier in the single node part. So in this part, the best split will pertain to 0.163 because it has the least value compared to 0.468 and 0.167. So that means you have to split your branch into three, into the following method: family, sports, and luxury. Okay, so that's for the Gini index. How about for the entropy? So a lot of researchers would utilize entropy, but I would still say that it would be very dependent on the study itself, because maybe the Gini index will work better in your kind of data, but some says that Gini index does not make a lot of wonders because it's too basic. That's why a lot of the researchers utilize entropy. But just to show its formula as well, in its formula, we'll just utilize the same example from earlier. So we just have to include log. So that would be log negative, then probability plus log. So total is 6. For this part, we just have to do what we've done earlier. And then we just have to change our values. So that would be negative 0 minus log of 0, because we have to copy this one as your value here, and then here as the value of your log. And then we'll have a base of 2. And then similar to this one, let's just copy here, negative 1 times log of base 2 with one value. So similar to the concept of Gini index, if we have at least 1 0 in our classes, then that means we'll also be having 0 value in our impurity index. And then for the second part, we just have to apply the same formula. So negative 1 over 6 log of 1 over 6 base 2 minus 5 over 6 log of 5 over 6 base 2. And so is the rest. And if we're just going to talk about the single node, the um best node would still be this one, because we're talking about the least value, and then the worst would be this one. That means we have to, most likely in the end, we have to branch out this node into a lot of sub branches afterward. And then for this one, we just have to stop. But how about the computation of gain? So the computation of gain is also similar to that one. So we just have to, okay, so we just have to change these values. For example, okay, so for example, in the computation of parent, so in our parent, a while ago, we have utilized 7 over 5. 7 plus 5, that's 12. So this time, we're going to compute it as 7 over 12, negative 7 over 12, multiplied to log of base 2, and then 7 over 12, minus 5 over 12, log of base 2, multiplied to 5 over 12. So that's how you can compute the Gini. So the Gini would be different here, because these will be a different scenario. And that's how you can also replace all the values here. The Gini will be different for your node 1. And then for node 2, it will also be different. So just to put it here, for example, in node 1, we have mm, negative 5 over 6, because the total is 6, log of 5 over 6 base 2. And then minus 1 over 6 log of base 2, also 1 over 6. So your Gini for N1 will be the value of this one. How about for N2? The Gini for N2 would be pertaining to this one. So that would be 2 over 6 log 2 over 6 Don't forget the negative value. And then another one would be negative 4 over 6 log of 4 over 6. All right. And you'll also gather a different value, not this one. And how about for the weighted entropy of your N1 and N2? You just have to apply the same principle here because we have the similar sum. We have 6, and then we also have 6 here. So that means you just have to replace this one with the value you got from this part, and then replace this part with the value you got from this part. So Gini N2. And then in the end, we just have to follow the same formula. P parent of entropy index minus parent of the offspring index. And that's how you can apply or you can find the gain. So similar to the Gini index, if we're looking for the gain or the best attribute split, then we have to find the highest value of the gain. Okay. But how about for the misclassification error? So the misclassification error only has a different value as well. Oh, sorry, only has a different formula. So they only differ in the formula, but their concept is pretty similar. So in this part, you just have to find the maximum value between your two probabilities. So in this part, the maximum value between these two is 1. So that will mean 1 minus 1 is equals to 0. For the next part, the higher value would be, of course, the 5 over 6. So that will mean 1 minus 5 over 6 is equivalent to 1/6. And then for the third node, the higher value between 2 over 6 and 4 over 6 is 4 over 6. So that means 1 minus 4 over 6 is equals to 1/3. And the best, the best value would still be equivalent to 0. Because this is the lowest part, that means this is the best node among all the 3 nodes. But you might wonder because we somehow have a similarity when it comes to applying these 3 methods. It's like this is always the best, the first node, but it would be different once you have a lot of latent variables and a lot of nodes to be considered. And we can also do some interchange within the data because in random forest classifier we'll be going to talk about the testing set and then training set. So definitely if we iterate them several times, the best impurity will also be different. Mhm. Okay. But what if your decision tree has too many branches? Because sometimes we cannot really stop them from branching out because it will just really stop unless your code, unless you state on your code that you wanted to stop your branching. That's what we call as pruning. And its primary example of primary usage is to handle overfitting because if we branch it out, if we branch it out into many kinds of nodes, most likely we'll receive a very, very high accuracy. But in the end, it's very prone to overfitting. So we have to be keen on details when it comes to finding what's the optimal code. So later on, we'll also discuss that when it comes to the code itself. So for example, when it comes to pruning, instead of branching out into different kinds of nodes here, so we still have one node, two nodes, and with other leaf nodes. But we can just branch it out into cutting off all these trees. It's actually possible because, for example, if your objective is to find not being able to loan when it comes to your income, for example, your income is $30,000, then that means you won't be able to loan if your income is below that amount. If your primary objective is to just find this no loan with the least number of branches, then we can just cut it out and just mention like this one. And then focus on the higher value that allows us to loan, like this one. Okay. So, but what is the main purpose of random forest classifier and decision tree? So we mainly use random forest classifier if we wanted to classify our latent variables, simply when we want to find the order between them. So let's say is in your data, let's say is the perception of one person better than the other latent variable? Mhm. I'll open that one. For example, if your U is better than the PV or your PV is better than the PS, and what is the best chronological order for all those attributes that you have? And of course, among all those attributes, we also have to consider what are the best classes, because in this study, we have continuous variables. So it's not like this one where we can just have dummy code. Like for example, we can just dummy code it as hot for one, mild for two, three for cool. So in our data, it's continuous. So if it's continuous, we'll have another separation and another coding for that part. So we can have, let's say, we have continuous variables from 1 to 5 or from 0 to 5. No, from 1 to 5 only. And let's say you have a value of 1.2, 1.3, 2.4. So in the coding, it will also find the best split range among all this. Maybe the best split for the first node, for this one, for example, the best split would be from 1 to 1.5 for this one. How about for this one? The best split would be probably around 1.51 to, let's say, 3.5. And then for the next node, we have a good split of 3.51 to 5. So we'll also apply Gini index, another Gini index or another entropy in this part. That's how the code will run if you have continuous data. Okay. But when we're talking about just one tree, for example, just this tree, we're only talking about the decision tree. And what's the main difference of the random forest classifier and decision tree? For random forest classifier, it has multiple trees. So that's the primary difference between the two. You can utilize decision tree only if you have minor problem and lesser number of variables. But if you have variables, so many variables like the one utilized for SCM part, will utilize random forest. So this is how the random forest looks like. And this will be your IV or your ID. So it's a combination of different trees. Okay. So any questions up until this part?
Before we continue to next week
Mm-hmm.
for the computation.
Oh,
Okay, no
it's
questions from
actually
me.
all.
Mhm.
Okay, it's already okay, Doc Yogi. So the next part would be about the coding.
Yes, I think so. But we can split into next week. Let them
Okay,
let them how is that process
yeah.
the
Yeah, maybe it's too much right
yeah,
now.
it's too much. It
Okay.
yeah, even for me, what no coding again. No, the code is already there. Omar.
Mm. Yes, it's there.
The code is already there,
So,
but you have to play around with anaconda,
yes, yes. But yeah, any questions for the competition, or when should we use, when should we not use?
Can you
Oh,
show
yes,
like
speaking of
one
that.
example of the publication that used RFC? Just show them so let them understand.
Oh, okay. Oh, sure. I'll show Ardvin's paper
Yes, okay. Just one
because
any random paper.
yes,
Yes, yes, yes.
Ardvin paper is really good.
Mm.
Oh, is my screen showing, Dr. Yogi? The one on Google Chrome?
Not yet.
Oh, okay. Mm, oh, I'll pick another one. The quality is low.
Okay, just show one. Yeah,
This one.
the result. Yeah,
Okay.
the random forest
Oh,
classifier result, RFC
all right.
result. Yeah, this one.
Okay. So, all right. So for this one, mm, I'll find the example.
But this is already the optimum one, the optimum
Yes.
RFC. No, the bottom one is the ANN.
Okay. So for this example, Ardvin pruned this part for sure. That's for sure because he
Of
has
course.
yes he has a lot of as we can see he has 1, 2, 3, 4, 5, 6, 7, 8, 9. He has 9 constructs. So if you have 9 constructs, you must have 9 levels as well. So 1, 2, 3, 4, 5, 6. Oh, we only have 5 because these one pertains to our leaf nodes. It only has 5, meaning he found that these 5 attributes are the best combination for his random forest classifier. And if it's correct, x1 is equivalent to mm, PV, this one, perceived vulnerability. That means before this one, you have to check there's actually a hidden which the decision tree does not show. There is a hidden branch here which pertains to your target variable. So if your target variable is, let's say in this study, it's, I think, perceived usability. So let's just say it's perceived usability. There is a hidden PU here. So this is your PU and then your classes from 1 to 5. From 1 to 5 in continuous variables. And in another one, you also have another decision tree here. So another branches that we have over here. But it will only show the most optimal random forest classifier, which is this one. So that means the topmost part is the most important variable. In this case, it's perceived vulnerability.
Vulnerability.
And yes, and it found that I'm not sure if Ardvin used Gini and entropy, but in your study, you can actually compare them. It's already a good study. Let's just say you won't utilize SEM. You can just compare Gini versus entropy. It's already a good study. Or
Yes.
instead of comparing your random forest to SEM and even to ANN. It's already good once you've compared a lot of factors when it comes to random forest. And then that means from values of 195 to 205, these pertain to your data. And then the class would actually pertain to another set of data. Let's say another set of data. It actually does not show what kind of class is it because maybe your class is around 3 to 5. Let's say 3 to 4 for high because I can see very high here. And then very high, that means Likert scale from 4 to 5. So we're not really sure up until this point what kind of partitioning the random forest classifier was able to show. But then as long as you can show this part, there is nothing to worry about that. And then the next most important variable would be x0. The x0 is most likely the topmost construct that's understanding the COVID-19. This one. And then the next part would be x1. So if you notice, it only varies between x1, x0, x0, and x0 for the for some of the branches, but not all the branches, because in this part we can utilize x2 and then it also utilize x3. So in random forest, it's totally okay to repeat all any kinds of your latent variables. So that means if there are repeating variables, it also means that some attributes do not bring contribution at all when it comes to the chronological order of your data. So that would definitely mean how strong your X1 is, because we can see that X1 is repeated multiple times here, and so as X0. But
That's the
between them,
difference, you know, everyone between
mhm,
the RFC and the decision tree. Everyone, you got it. Because now, you know, you can see why there is that one again, and again. Yeah, because we utilize the random forest
mhm,
classifier. Yeah.
mhm. Yes. So in contrary, when it comes to SEM, you get to somehow check the variables one by one, but in random forest, it would you can use random forest if you wanted to focus on the most important attributes. But if you wanted to focus on each attribute, definitely SCM is a better tool. Okay. So we have a total of 1, 2, 3, 4, 5 levels. And then did he mention the class? Oh, okay. So he mentioned that the very high and high class would pertain to this part. So most likely as we've talked about earlier, maybe around 1 to 3 and then 3 to 5 class. We're
Yes, yes,
not
yes,
really
yes, yes.
sure what would be the partition, but based on the explanation, if it's high, this one. So if it's high, that means high perceived vulnerability for the topmost part. If it's very high, then that means very high understanding of COVID-19 for this part. And for this one, not so high for the false, which kind of makes sense because if you have a very high understanding of COVID-19, then most likely it will lead you to these underlying principles unless your answer is somehow on the lower level, which is just high for this part. So
We
in the
can, yeah,
Mhm,
we can continue this one by next week, perhaps for the, you know, the this one, like perhaps for him, like
mhm,
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you know,
mhm,
like we can check the Excel file, you know, like later on how
mhm.
he actually
Oh,
like you know, at how like very high, and then like
mhm.
normal perhaps.
Yes, yes. And I think it would be better if we're going to utilize the Turkey earthquake
Yeah, Turkey
in the
earthquake for
coding.
next week. Yeah, in the coding. So
Much
everyone will
easier.
understand
Mm,
100%, you know, like for that. Okay,
mm.
for this evening. Yay!
Okay,
Let me stop
yes,
the
that's it.
recording.